When a wild detail gets
I actually don't know. Let me do a Google.
All right, welcome back to 353. We have officially survived pretty much the whole year. So this lecture will probably be a new record. You can stop me if you want me to slow down or do anything, but everyone liked the scheduling questions, right? This is the second half version of scheduling questions. So, should be, again, new record. So, we are talking about page replacement. So, to, recap, I guess, architecture courses or organization, computer memory hierarchy is always a trade-off of capacity and speed. So, at the top, we have as our fastest things your CPU, specifically your CPU registers. There's not that many of them, but they are very fast and kind of expensive. Then as we go down this pyramid, our capacity increases, but our speed decreases, and usually our price. So below that, we have cache on our CPU. This is your L1 cache, your L2, possibly L3. That is unrelated to how we name levels of page tables. So there's your CPU cache, and then after that, you have your memory or your RAM. It's a random access memory. It's volatile, so if you unplug the power, you lose all your data, but we don't really care about that. It is basically a cache for your CPU. That's where all the data you feed your CPU comes from. And then below that, we have non-volatile memory or NVMe storage, which are like the fast SSDs that most of you should have in your laptops. Then below that, we have old SATA SSDs, which you might have in your older computers. So those are another variation of solid-state disks. Then we have our hard disk drives, which are the spinning metal things you've probably never seen before, but that's what was in the first gen iPod. I guess iPods don't even exist anymore, but that is what was in that. Or, if you want to buy like 20 plus capacity drives, you should buy something like that. And below that are tape drives. So none of you know what the hell a VHS tape is. You might have heard it as like some weird retro tech thing. But in fact, data, lots and lots of data is archival data stored still to this day on tape drives. They are magnetic tape drives that you have to like unwind and spin and everything. They are very, very slow, but they're very cheap, and you can buy them at like, I forget the price, but the price per terabyte is very, very low. But they're very, very slow. That's where like Google archives the entire internet. They archive it on tape drives. If you go at the data center, you'll see some machine that physically takes tapes out of a cassette thing and puts them in so it can read them. So it's very, very slow, but you can buy it for like pennies per terabyte or something like that. Probably not that cheap, but along those lines. It's just way cheaper. And believe it or not, still in use. You probably will never see one, and neither have I. But the whole goal of this is we want to hide this hierarchy from the user. So each level wants to pretend it has the speed of the layer above it and the capacity of the layer below it. So that means if we're doing it for memory, we want memory to be used by all processes actually to exceed the amount of physical memory we have. Because, well, we can take advantage of the fact that not all of them are going to be in use at the same time. So we can only keep pages in memory if they're being actually used. And the whole idea behind this is we can use the disk as we can use memory as a cache for disk. So if a page isn't being used for a long time in memory, we can kick it to the disk and store it on the disk, and then of course it will be slower. If we need to get that memory again, we have to load it from the disk back into memory. But we can actually use more memory on our computer than we actually have physically on our machine. And the process of doing that would be swapping pages back into memory when they're needed. If you're on Windows or anything like that and you notice a big file on your C drive, if you look at the hidden files, there's something called, I forget what they call it, I think it's just called a swap sys file or something like that. That's what it does. It's just storing pages, like using your disk to store pages of memory that aren't used for a while. So, even with if you even had 8 gigabytes of RAM, what year is it? Well, you can still use Google Chrome with like 2 tabs open that uses 10 gigs of memory, because some of that information can go to disk. So what the typical system is we currently use is called demand paging. So we're using memory as a cache for the file system. What we can do is map memory pages to file system blocks. So some blocks will not be used. And again, we'll only load them into memory when they're used through the page fault handler we saw previously. So if you're trying to access that memory, you get a page fault, the OS can go ahead, or the kernel specifically can go ahead, pause what's going on, load that page into memory, and then resolve that page fault and transparently just let you use memory. So what it can do is if the page doesn't represent a file, what we can do is map it to swap space. So if we just have memory we're just using for, I don't know, just random memory for our machine, we can map it to swap space. So that would be like that big swap file. If you're using Windows, or Mac has an equivalent, Linux has an equivalent as well. And then just move it to disk if we need more physical memory for other programs on our machine, or if we don't have to load a file in or anything like that. So a process's working set, that's our only fun definition for the day, should fit in physical memory. So what a working set is given an amount of time, it's the number of pages your process uses. Well, that's called its working set. If its working set is not all in memory at once, then your program is going to go very, very slow because it can't fit that working set into physical memory. Your process will do something called thrash, meaning the pages will go back and forth between the disk and memory over and over again, and it will make your program even slower. So we want to avoid that at all costs if you care about performance at all. So specifically, what we get to talk about today are things called page replacement algorithms. So we're assuming we have pages on disk, and we only have a set amount of size in our memory. So we have to pick and choose which pages we kick out of memory and throw them back to disk. So there's a few page replacement algorithms. In fact, this is actually simpler than scheduling. So there's the optimal, which is replace the page that won't be used in the longest. Again, like with scheduling, we look into the future, see the page that's not going to be used in the longest, and replace that page. We could do random, so replace a random page. We could do our friend, first in, first out. So pick the oldest page first that we brought into memory and throw that one back to disk. Or we could use least recently used, so replace the page that hasn't been used in the longest time. So that's using the past to predict the future. So to evaluate it, this is how all the questions will look like, similar to the scheduling questions. So we'll assume our physical memory has some very silly limit, well, some limit that's hilariously small, because we want to be able to do these questions in a timely fashion. So we can assume it only holds 4 pages in total in memory, and we access the following. So these are all the pages that are initially on disk. I'm just going to give them a number. So same number means same page. So this is page 1 on disk, 2, 3, 4, 1, 2, 5. So in total, there's 5 pages we're accessing on disk. We're keeping track of what pages are in memory. So initially, none of these pages are in memory, and we only have space to hold 4 pages. So we'll use this order of access for a bunch of examples during the lecture. And the whole goal here, unlike with scheduling, is pretty straightforward. We want the fewest number of page faults where we have to load data in from disk in total. So for every example, we will find the number of page faults. So how I'm going to do this is for every access, I will draw a box. So this box is all the pages that are currently in memory. And at the top of the box is going to be the page we are going to access. So initially, we assume nothing is in memory, so the box is empty. It could hold 4 pages or 4 numbers. And on my first access for page 1, Well, in order to use it, I have to bring it into memory. So I put a 1 in here in memory, and I put it in red because it had to come from disk into memory. So everyone okay with that? All right, the next 3 steps are going to be very boring. So if I access page 2, same idea. I access page 2. I could kick out page 1. There'd be no point to it because I have 4 slots. I can hold other ones. So I can read page 2 in from disk to memory. Again, I would put it in red here, indicating that, hey, that was a page fault. I had to read it from disk into memory. Everyone still good? All right, so same thing happens for page 3 and page 4. This is pretty much what's going to happen in all the examples. Do I have permission to skip this for all the examples? Plus 10 minutes. All right, so now when we access page 1, we don't have to worry about it, right? So we access page 1. It's already in memory. Again, this box is what's in memory. So there wouldn't be a page fault. I don't have to do anything. A page fault means I have to kick one of these pages out of memory and move it back to disk. So if I access page 1, it's already in memory. I don't have to touch it, right? So in that case, I put a 1 that I'm accessing, and I keep all the numbers here, and I don't write any of them in red because they were already in memory. I'm all good. So everyone still good? All right, what's going to happen when I access page 2? Same thing, right? I access page 2, already in memory. I don't have to do anything. The fun comes in when we access page 5. Oh no. So we access page 5. So we want to bring that into memory. So we have to replace either page 1, 2, 3, or 4. So this is why it's called page replacement. So if we are doing the optimal thing, that means we are accessing 5. It means we are looking into the future, and we are replacing the page that is not being used in the longest time. So if we look in the future from the access for 5, should I replace 1? No, because I use it right after. Should I replace 2? No, it's used right after that. Should I replace 3? No, it's not. It's used after that. Well, at that point, I only have 1 victim left in memory, so it's 4, so I just need to get rid of 4. So we are kicking out page 4 for page 5. Yes? All right, so how I would write that is access page 5, and I'm kicking out page 4, so I'm removing it, whatever you feel like, and then writing page 5 in red because I had to bring that from disk into memory. Still good? All right, well, we did the optimal thing. We access page 1. We don't have to do anything, right? We did the smart thing. So just write it as an access. Again, access page 2. Don't have to do anything. We already have it in memory. Access page 3. Don't have to do anything. It's already in memory. OK, now we access page 4. We have to kick out something. What are we kicking out? 1? Everyone agree with 1? Can we kick out 2? Can we kick out 3? Can we kick out 5? Yeah, pretty much we just don't want to kick out 5, right? Because 5 is the next one we're going to use. In this case, we would accept all answers because as long as you don't kick out 5, you're good. Most people seem to hate 1 for whatever reason. So we can kick out 1 for page 4. Again, write it in red. Then our last access is going to be 5, and we're done. So we're done. The last thing we have to do is just count the number of page faults. Since we've done this, it's basically count the number of red numbers. How many red numbers are there? 6. So again, you can have a non-programmable calculator if you want to add this if you want. Probably shouldn't need to. So at the end, 6 page faults. This would be done. So this, again, looks like scheduling. So questions about that? All right, let's do this like 6 more times, and then we'll call it a lecture. Maybe not 6. All right, let's do FIFO. So reset it again. Same order of operations. We're going to do FIFO, full first in, first out for the replacement. So like you've given me permission to do, I can skip the first 4 accesses because I have to bring them all into memory. So those are our first 4 accesses, again, loading them from disk into memory. So now we access page 1. Again, that's already in memory. We're good. We don't have to do anything. Same with page 2. It's good. It's already in memory. We don't have to do anything. Now, oh no, we access page 5. We have to replace something. If we are doing first in, first out, what is the first page we loaded into memory given everything we have here between 1, 2, 3, and 4? 1, right? So we loaded 1 first. So we kick out page 1 for page 5. So it would look like this, right? Okay, now we access page 1. Crap, it is not in memory. I have to kick out something. What am I kicking out for page 1? 2, the next oldest, right? So I'm kicking out page 2. So, oh no, this seems crappy. Now I'm accessing page 3. Or sorry, now I'm accessing page 2. What do I kick out? Page 3, right? So I kick out page 3. Oh no, now I access page 3. What do I kick out? I kick out now 4. So now it looks like this. And now I access page 4. Oh no, this seems like the worst thing I could have done. All right, so now I access page 4. What do I kick out? Well, now the oldest one is 5. So I kick out page 5. Oh, now I access page 5. Wow, this is the worst thing I've encountered. So now I have to kick out something for page 5. In this case, I'd kick out page 1 again. So it should look like that. And yeah, if you want to do first in, first out fast, all your page faults will be diagonal lines. So all your red numbers should be in diagonals. So they might be spaced out. Like here, there's a space between 2 of them, but the page faults will always be in diagonal lines. So top to bottom, if you want to do it fast and not even argue about it. So this was pretty crap, right? So how many page faults were there? 8? 10. All right, good thing we'll have a calculator. So 10, that's pretty terrible, right? So let's have a little bit of a thought experiment. So how many page faults would I have if memory could hold, let's say, 5 pages? None? 4? 5, right? If I could hold 5, I would just have, page fault on the first axis to every page, but I can hold them all in memory, right? So it makes sense. If I have 5 pages, that also means I have more memory. If I have more memory, I should have less page faults, right? Makes sense. So it should make sense that the opposite is also true, right? If I have less memory, I should have more page faults. Okay? Everyone agree with that? Makes sense. All right, so we'll do the same thing again. So let's put that theory to the test. So we'll do first in, first out, where our physical memory can only hold 3 pages, so less than before. So we had 10 page faults before. Let's do this again. So I can skip the first 3 accesses. They're going to be boring, right? So 1, 2, and 3, all not going to be in memory. So let's see if we can do this fast. So I access page 4. I'm out of memory. I can't just load it. I have to kick something out. What do I kick out? 1 by waterfall method, right? Ooh, that seems bad. So now I just kicked out 1, and I access page 1. Before, this was a hit, right? I didn't have to kick out anything. So it's looking like our theory is correct. So I access page 1. What do I kick out? 2. I access page 2. What do I kick out? 3. Yikes, I'm 6 for 6 so far. Now I access page 5. Well, I have to kick out something, right? I have to kick out 4 by waterfall method. Now, thankfully, it finally got a hit, so I access page 1. mercifully, it's already in memory, so I don't have to do anything. Also for page 2, page 2, already in memory, don't have to do anything. Page 3, not in memory, I have to kick something out. What do I kick out? 1 by diagonal method. So 1 is our next victim here, so I'd kick out 1 for 3. Now I access page 4. What do I kick out? Kick out 2, right? Kick out 2. Then last access, I access page 5. And that's a hit. How many page faults are there? 9. You all lied to me. This is less. So, if your computer is ever running slow, just take out a stick of RAM. Right? This is better than before. This is only 9 page faults. We had 10 before. What the hell is going on? That's the worst advice you would probably ever think of hearing, but technically, in this case, it worked. So, what we encountered is Bellidy's anomaly, which says more page frames, so more memory, can actually cause more faults. This is a specific anomaly with FIFO algorithms and FIFO algorithms only. So, unless your operating system is implemented very poorly, that advice I just gave you actually isn't true. So, it does not exist with least recently used or quote-unquote stack-based algorithms. In fact, if you like math and Greek letters, someone proved in 2010 that anomaly is unbounded, which basically means you can construct a sequence to get any arbitrary page fault ratio you would like. And for other algorithms, we don't have to worry about this because what we thought initially was true. If you increase the number of page frames or get more memory, that decreases the number of page faults. So for everything else, it makes sense except for FIFO, which is also why FIFO is especially bad for page replacement. So, fun little anomaly. Fun for some definition of fun. All right. So, last example before our first break. We are steamrolling here. So we're going to do least recently used. And in case this was multi-processing, we could use FIFO to break ties. In this case, we won't have any ties, so we can just not worry about that. So we'll go back to memory can hold 4 pages and our accesses. So again, first 4 accesses, they're going to be faults. We have to load them into memory. So we argued about that again before. We can skip that step. Now we access page 1. Again, already in memory. Don't have to do anything. Access page 2, already in memory. Don't have to do anything. Access page 5. So now we have to find something to kick out. So least recently used means we will look backwards to try and predict the future. So if we do least recently used, we try and find the page that hasn't been used in the longest. If we go backwards, 2 was just used, so we should not get rid of 2. Well, 1 was used right before that, so we shouldn't get rid of 1. And then we also shouldn't get rid of 4. So we only have 1 victim left, so if we use least recently used, we should kick out page 3, right? Isn't this a joy? Brings us back to those good memories of scheduling before Thread screwed everything up. So, everyone okay with that? We replaced page 3 for page 5. All right, so in this case, now we access page 1. Hey, it seemed to work this time. So page 1, already in memory, don't have to do anything. Page 2, already in memory, don't have to do anything. Page 3, oh no, not in memory, I have to replace something. So again, I can look back at the past. I can't replace 2, can't replace 1, can't replace 5. So that only leaves me with 4 as my victim. So everyone agree? I have to get rid of 4. All right. Screw 4. It's replaced by page 3. So again, write it in red. Now, turns out that was a bad idea. My next access is page 4. So I have to get rid of something. What do I get rid of? 5. All right. So if I look back, can't get rid of 1. Can't get rid of 3. Can't get rid of 2. Can't get rid of 1. So I can only get rid of 5. So this was looking so promising, But now I have to get rid of 5, replace it with 4. Now I access page 5, which I just kicked out. Oh no. So now if I look backwards, I can't remove 4, can't remove 3, can't remove 2, so I can just remove 1. So this is what it would look like. And again, if I count all my page faults, looks like I have 1, 2, 3, 4, 5, 6, 7, 8. So 8 page faults. So wasn't as good as optimal. Optimal is 6, but it's called optimal for a reason. Can't do better than that. First in, first out for this got 10, so this landed somewhat in the middle, but we could kind of actually implement this-ish. So speaking of implementing it, if we tried to implement it, this would actually be kind of a pain in the butt because it has to search all of the pages. So how you could implement it was you could keep like a timestamp or a counter for each page. Every time you reference a page, just update the timer. So like you could save the system clock into that counter. And then for replacement, what you would have to do is scan through all the pages and find the one with the oldest clock. And that's the oldest one, so you get rid of it. Any other ideas how we would implement this faster than this? Yeah.
Having some sort of indicator of which one is the oldest after every axis.
Some indicator of which one's the oldest? What would your indicator be, or what would you use?
Like a flag of some kind.
A flag? So how would you keep track of, so you just give one page a flag?
Yeah, and then like with every new axis, then you would go back to.
So with every new access, I'd go back to and reset the flag, and then
Set the flag to like the oldest one.
you kind of keep track of the oldest one. I see where you're getting. You're very close. Think of a fun data structure that is in constant time. Hash table. No. This is. Yeah. What would we be hashing to and from? Yeah. Yeah, a linked list, and we can keep the oldest one at the head or the tail or whatever, and just keep on adding to it, right? It's actually an appropriate use for a linked list, believe it or not. So you could create a doubly linked list, which kind of is your idea of flags, except, well, the flag is whoever is at the front of the linked list, right? So if I had a doubly linked list of pages, for each page reference, I could move it to the front. So in this case, my newest one would be at the front, my oldest one would be at the back. But you could reverse that if you really wanted to. So for each reference, I could move it to the front of the list. And then for replacement, I can remove the page that's at the back of the list. So my newest one's always at the front. Therefore, my oldest one is always at the back. But if I were to implement this, it requires, in the worst case or in the average case, 6 pointer updates for each page reference. So changing the previous and next pointer of 2 nodes and possibly the head and the tail of the linked list structure itself. So on every reference, even if I read a single byte, I have to do 6 pointer updates. Very bad trade. Even though it's a constant time operation, the constant actually matters. So 6 pointer updates is going to be way too much if I'm only accessing a single byte. And also, you should more or less be done with parallelizing your hash table. Imagine parallelizing a linked list, the locks you would need for that to make sure it is safe, pointers all over the place. Yeah, that would be even more fun. So it would need a lock to make sure that it is all free of data races. So it would probably be under high contention too, because multiple processors use memory, and it would probably be a very bad idea. So implementing it in practice isn't going to work. So what we are going to do is actually implement some approximation of least recently used. And the whole intuition behind that is least recently used is an approximation of the optimal case. So an approximation of an approximation is exactly what operating systems is about. So there's lots of different tweaks you can do to implement it more efficiently. Specifically, what we'll look at after the break is something called the clock algorithm that tries to approximate least recently used. but there's also least frequently used, so you keep track of less information, try and estimate it. 2Q, which tries to do that idea in hardware, or adaptive replacement cache, which is way too complicated for an intro operating system course. So we'll get to that. The clock algorithm, when we come back from the break, we literally get to draw a clock. It will be lots of fun. So before we go on our break, just remember that whole idea of page replacement algorithms is to reduce the number of page faults. We start off initially with pages only on disk, and we are trying to bring them into memory. There's only so much capacity in memory, so when it gets full, we have to kick something out. So the algorithms we saw so far were the optimal. Good for comparison, not realistic. That's looking in the future, kicking out whatever page is not being used in the longest. Random actually works surprisingly well. It avoids the worst case. It's better than FIFO for the most part. FIFO, it's easy to implement, but has that weird anomaly, which we really don't want because that is very strange. And least recently used, it gets close to optimal, but it would actually be expensive to implement in hardware. So let's take our 10-minute break, come back, and we will draw clocks for the remainder of the time, and it will be fun. And I guarantee it will be on the final. Again, it will be like the scheduling question. We shall rejoice. Alrighty, we're back. So we can do the clock algorithm and get out of here. Oh yeah, also, the final exam's like the 30th, right? Yikes, that's terrible. So, already ahead of time, I propose canceling the last Monday and instead I'll stream a review session closer to the 30th because it's like a month later, yes? Yay, okay, great. I don't want to come here Monday anyways. Not next Monday, the one after that, the last Monday. All right, we'll do that instead because, yeah, if I do review then, you'll just watch it again closer to the 30th, probably the 29th anyways. So I'll stream closer to that, like 28th, 27th, 28th, 29th, one of those days. So let's do that instead. Again, like I said, the course gets easier as we go on. We've survived the hard parts. So let's go into the clock algorithm. Guaranteed it'll probably be on it. So still page replacement. The data structures we are going to use here are, we're going to keep a circular list of pages in memory. And what this will do is use a reference bit for each page in memory. So I will put it in light gray on the next slides. And that reference bit is the only thing that's going to be updated when we reference a page. So we can't go any faster than that, just flipping a single bit if we access our page. It's about the fastest thing we can do when we reference a page. Again, that is going to be our bottleneck. Our slowest operation is what we do when we reference a page. So we'll do this. In fact, this is what is already handled for you by the MMU. It will set that for you whenever you access a page. It will update a reference bit for you. So the other data structure it has is the hand. So it's just an iterator pointing to the last element examined or last page. So how to remember what happens with this is whenever you reference a page or use a page, if it's in memory or not, you're only updating a bit. You're not doing anything more than that. The algorithm only runs when you are doing page replacement, when you're figuring out something to kick out. So when you're figuring something to kick out or to insert a new page, the hand is pointing to a page already in memory. So you check the reference bit of that page. If it's 0, that means it hasn't been referenced recently. So you evict that one, you kick it out, and you place the page there and advance the hand. We advance the hand because, well, what's going to happen is if the reference bit is 1, we set it to 0 and then advance the hand. So we essentially give it a second lease on life. So we just flip the bit from a 1 to 0 and then find another victim to evict. So that's why we advance the hand, because if we didn't advance the hand after we insert a new page, we would immediately try and replace whatever we just put in, which would go against the whole idea of approximating least recently used. So that is why we need to advance the hand after we replace the page. And then again, for page accesses, like I said before, all we're doing is setting the reference bit to 1 if it is not already. So this is how we would do it with a diagram. So you should probably have this on the scrap piece of paper beside it. And again, just to save me some time, I'll just make fewer page accesses. Just so, again, I don't have to write this damn thing over and over again. So we'll assume physical memory can only hold 4 pages. And initially, nothing is on the disk. So how I draw the clock initially is I draw a box for every single page. And at the top, that's the number of the page currently in memory. And then the light gray box is the reference bit. So currently, I just put them all as 0 because there's nothing currently in memory. So let us do this. So if I go through it, our accesses, starting off strong. For some reason, I can't write when I stand up. So the accesses are 1, 2, 3, 4, 5, 2, 3, 1, 2, 3. So again, like I had before, I could draw a box for every single access like that and put in what's in memory and what is not. So I'll have my first 3 page accesses here. And then to the corner, I can draw the clock. So 0, 0, 0, 0, 0, 0, 0, 0, and I can just add in each page pointing to the next page in the list, going around in a circle. Again, you can draw it, it looks kind of like a clock. And then the hand, which is just the iterator that is the current victim for eviction. So this is what it would look like initially. Everyone okay with my amazing drawing? All right, so if we follow this, we access page 1. We have to find a victim because it's not currently in memory. So we would follow the clock algorithm. So what it would do is I inspect the page this iterator is currently pointing to. Its reference bit is 0. I don't care what page it's in. In this case, it's an invalid page anyways. But it means I'm getting rid of that. If it was something, or if it's just 0, that's what I'm using to replace it. So the steps are, I picked my victim. So I'm inserting page 1. And I would also make its reference bit a 1. And then the final part of it is I would advance the iterator. So I should point to the next element. So I advance the iterator to point to the next element. And then if I were to draw it in the same box before, well, I brought 1 into memory. So everyone good with that? All right, so again, if I do 2, I access page 2. It's not in memory, so I have to kick something out. Well, the hand's currently pointing to this invalid page. Its reference bit is 0, so I kick it out. So I replace it with page 2, set its reference bit to 1, and now it is replaced. Still follow me on the same page? I have to do that joke every year. It is in my contract. So, did I forget to do anything before I go on to the next one? Yeah, I have to advance the hand, right? Otherwise, I'd be trying to kick out page 2. Probably wouldn't want to immediately have a strike against it. So, advance the hand before I start the next access. Now I access page 3. Oh no, I have to replace something. Currently, the reference bit is 0, so I kick that out, update the hand, and now 3 is in memory. 1, 2, 3. So now I'm accessing 4. So same idea again, right? So same idea again. Its reference bit is 0. I replace it. It's now page 4. Reference bit is 1. Advance the hand. So it would look like this. And let's get rid of this. All right, so now I access page 5. Oh no, I have to kick out something. This is going to be more fun. So if I write it in my handy dandy boxes here, I'm accessing page 5. And I have to pick one to kick out. So if I follow the clock algorithm, I'm going to first inspect the page that my hand is pointing to. So it's page 1. What's its reference bit? 1. So I do not kick it out. All I do is I change its reference from a 1 to a 0, and I advance the hand to try and find a new victim. All right, what do I do here? Same thing, right? Its reference bit is 1. I can't kick it out, so I change the reference bit from a 1 to a 0, and then update the hand. Same idea. Pointing to the next one, its reference bit is 1. I change it from a 1 to a 0. I'm not kicking it out. Then I update the hand. Same thing with 4. Update it to a 1 to a 0. Advance the hand. And now I'm pointing to the first page. Its reference bit is 0, so I'm kicking out page 1. Right? So, to show you a shortcut, so if I back up, I kind of just went around the world, right? Around the world, that was kind of boring. If you're in the situation where you're trying to do the page replacement, you're pointing to a node, and all of them have a reference bit as 1, they're all going to get changed to 0. If you want to do it fast in one step, just change all the 1s to 0 because it's going to go around and try and evict everyone. So if you want to do it fast, just change all the 1s to 0. Don't touch the hand. That's what's going to happen anyways. So you can shortcut it by doing that. Everyone like the shortcut? Perfect, because going around the entire time is a waste of time. So do that shortcut. Now we are pointing at page 1. Its reference bit is 0, so it is gonzo. So we would replace page 1 with page 5, set its reference bit to 1, and replace and update the hand. So we replace page 1 with page 5. So it would look like that. Now we access page 2. What do I do when I reference page 2 or use page 2? Yeah, well, I just have to update its reference bit, right? I want to be as fast as possible. I'm not going to screw with the hand. I'm not going to do anything. All I'm going to do is change its reference bit from a 0 to a 1, or a 1 to a 1 if it's already referenced. So it's going to be a page hit, but something is happening in the algorithm, so I should keep track of it. But according to the page faults, nothing happened. It was already in memory. Good? All right, so now I access, let's see, that was 2. Now I access page 3. So what do I do in this case? Change its reference bit, right? So change page 3's reference bit from a 1 or 0 to a 1 since I just used it. Otherwise, it was still in memory. So we have 5, 2, 3, 4. And you can kind of see how this works. So now if I look at this and I'm trying to replace something, well, I'm not going to replace 2 anymore because I just used it. Not going to replace 3 anymore because I just used it. Not going to replace 5 because, well, I haven't got to that point yet, so I must have used it recently-ish. So now when we get back to page 1, oh no, we have to kick something out, right? So page 1 is not currently in memory, so I have to kick it out. I have to follow the algorithm. So do I kick out page 2? No. All I do, its reference bit is a 1, so I change the 1 to a 0 and move the hand forward 1 to find my next victim. So now I'm pointing at page 3. Its reference bit is 1. Can't get rid of it. I change the 1 to a 0, update the hand. And now I am pointing at 4. Oh, its reference bit is 0, so that is my new victim. So I get rid of 4. I replace it with page 1. Its reference bit is 1. And then I remember to update the hand to just go forward 1. So in this case, I replaced page 4 with page 1. Everything else stayed the same. Now I access page 2. Access page 2. All I do is update that reference bit from a 0 to a 1. And that is it. It was still in memory, so we are all good still. So 5, 2, 3, 1. Now I access page 3. Again, same idea. It's already in memory. I update its reference bit from a 0 to a 1. So this would be my final chart at the end. And then if I want to count the number of page faults, let's count the number of red things. So there are 6 page faults. All right. Everyone good with that? Yeah?
So do you only advance the hand when you get like a page fault? Is that
yeah, you only advance the hand when you do the page fault because you're hoping that that's the rare thing. Doing that would be slow, but that's the exception, not the rule. The rule is the reference, and we only update 1 bit when we have a reference. Otherwise, it would be slow. All right, any other questions with that? So, also, you have it on the slides, so why it's called the clock. If you look at going through all those steps, one by one by one, where we initially put them in memory, and then here we could have taken our shortcut to set everything from a 1 to a 0, but if you go through it, it just goes around all the places, and we would eventually replace 1 with 5, advance the hand, access page 2, set its reference bit to 1, access page 3, set its reference bit to 1, access page 1, so we're finding a victim here, so not kicking out 2, not kicking out 3, we're kicking out 4, so insert it, advance the hand, then we access page 2, update its reference bit, and then 3, update its reference bit. So again, this is just the chart that you would draw alongside that I did correctly. So this is our 6 page faults here from that example. All right, so, oops, not that, not that. Oh God, struggle. All right, do we want to do that example, or are we tired? Who wants to do this example? No one. One person. All right, we can do it after, or it's on the slides. I guess I'll skip it. It should be on the slides or quick, or there's now lots and lots of clock replacement examples on exams because on the final it's pretty much always there, even going back to that UCLA course. So I'll leave that with you, and we can do it later if you want closer to the final. So as just another word of advance, for performance, you might choose to completely disable swapping. So typically memory is cheap and has high capacity. So rather than doing this and swapping things back and forth to disk, that will make your program run slowly. For some cases, you might actually care to be notified of this. And while page replacement, you'd have to ask your kernel if it's happening or not. Otherwise, if you have access to do that, otherwise your program's just going to be running slow. So what you might choose to do is disable that completely, disable swapping. A lot of people do this on servers. And well, if you actually run out of memory, Linux will run the OOM, or out of memory killer. That basically just sig kills the memory hog, and then boom, you have memory again. And we could also do different things with our virtual memory system to, try and speed it up. So we could have larger page sizes to allow for speed ups. So instead of a 4 kilobyte page, we could essentially get rid of the last level and then just make the L1 point to a 2 megabyte page instead of pointing to an L0 page table, which points to a 4 kilobyte page. So you might see on some systems, some operating systems are kind of moving to it because 4 kilobyte pages we've had since the 70s. So now the Linux kernel will use 2 megabyte pages. They're called huge pages, if you see that terminology. Or if we knock out 2 levels of page tables, each of the pages would be 1 gigabyte in size. Those are cleverly called gigapages. But the whole idea behind them is we trade more fragmentation for more TLB coverage. And what that is trying to say, remember the TLB is just a cache from virtual page number to physical page number. This is just saying if our pages are bigger, then for the same number of entries, we cover more memory. So let's say if we had 10 entries in our TLB and all our pages were 4 kilobytes, then across all of them, that covers 40 kilobytes worth of memory for those 10 entries. If our page size was 2 megabytes, then those same 10 entries would cover 20 megabytes worth of entries. So my program could use 20 megabytes of memory all at once without having to do those slow virtual page lookups or anything like that if I used huge pages, which might be advantageous to you. but your kernel typically does this under the hood. And again, the trade-off is going to be, well, if your program doesn't use all 2 megabytes, it's just some wasted space, which is what we call fragmentation. So, questions about that or anything else today? New record, hell yeah. So, the clock algorithm, it's an approximation of least recently used. The data structures are a circular list of pages in memory. Again, just draw a little circle. One links to the other. They go around in a circle. You'll be using a reference bit for each page in memory. I just put it in a box at the bottom. You can do whatever you want, but this would be managed by the MMU itself. It also just has a hand or an iterator pointing to the last element examined. And then the algorithm, which is only runs when we do replacement. This is the slow operation. We want to happen as least, we want to update the hand as least amount of times as we can. So only when we need to find a page to remove, we check the hand's reference bit. If it's 0, well, we place the page there, insert the new page, make its reference bit a 1, advance the hand. Otherwise, if we're pointing at something whose reference bit is 1, set it to 0, advance the hand and repeat until you finally find a victim. And then for page accesses, this is the fast operation. All we ever do is set the reference bit to 1. So if it's 0, it becomes a 1. If it's 1, it stays a 1. So all good? All right, I'll hang out here because I have nothing better to do anyways, but the rest of you are free. So just remember, pulling for you, we're all in this together.